Assalamualaikum and hi everyone. This is the title of our final year project. In this introduction, I will summarize all the key parts of our study. Firstly, objective and problem statement. In chemistry, understanding how atoms combine to form molecules is essential because it explains molecular shape, bonding, and chemical behavior. However, many students find concepts such as hybridization and molecular orbital theory difficult to visualize, especially when learning only from textbook and static diagram. Therefore, the main objective of this study is to develop a centralized online database that integrates molecular theory with digital visualization tools. This project aims to make abstract molecular concept clearly and more accessible, while supporting students in learning independently. Secondly, the significance of the study. This study is significant because it addresses a major challenge in chemistry education, which is helping students understand complex and abstract molecular concepts. By using digital visualization tools, students can better imagine three-dimensional molecular structure and electron distribution. In addition, this project supports self-directed learning and promotes the use of modern educational technology. The database developed in this study can also serve as a long-term learning resource for future CHM 361 students.
Lastly, hypothesis based on the challenges students face in understanding abstract molecular concepts. This study proposed that the use of digital visualization tools can improve learning outcomes. Therefore, the hypothesis of this study is that integrating a centralized online molecular database with interactive visualization features will significantly enhance students' understanding of molecular structure, orbital interaction, and electron distribution compared to traditional learning materials.
Molecular structure and chemical bonding are fundamental topics in chemistry and are included in CSM 361. However, students find concepts such as molecular orbitals, electron distribution, and three-dimensional structure difficult to understand because they are abstract. Molecular orbital theory and hybridization theory are commonly used to explain bonding, molecular stability, and geometry. Previous studies show that visual representation help improve understanding of this concept. Therefore, a structured and visual learning platform is needed to support student learning.
This slide explains the methodology used in developing the image and the online learning platform for this project. First, molecular wave function of the selected molecules were generated using the Gaussian suite of programs. Gaussian View software was then used to visualize the molecular structures, molecular orbitals, and electronic distribution. The image concepts were designed based on the objective of the study to ensure consistency with molecular orbital theory. Next, text-based prompts were carefully prepared to describe important molecular features such as atomic arrangement, molecular geometry, and electron distribution. The prompt also specified the desired visual style, including three-dimensional and color code representation. These prompts were processed by an AI model to generate the required molecule image. Several iterations were carried out to refine the image. The final image was selected based on clarity, visual quality, and their suitability for explaining complex molecular concepts. These images were then used as supporting figures in this project. In addition, this project involved the development of an online database focusing on molecular orbital architecture and electronic structure. Chemical and structural information was obtained from reliable sources such as ChemSpider, standard chemistry textbook, and peer-reviewed literature. Web-based molecular visualization tools were used to generate three-dimensional molecular models, orbital representation, and electron density maps. The selected molecules were aligned with the CHM361 syllabus. All collected information was organized into a centralized online platform with interactive visualization features to support self-directed learning. Finally, the platform was reviewed to ensure accuracy, clarity, and effectiveness in improving student understanding of orbital architecture and electronic landscape.
The main result of this project is the successful development of an educational website. The website covers key CSM361 topics such as molecular orbitals, hybridization, and molecular geometry. Visual elements like molecular diagram were included to support understanding of abstract chemistry concepts. This website was developed based on CSM361 topics such as molecular orbitals, hybridization, and molecular geometry. Visual representation were used to help students understand abstract concepts like orbital overlap and chemical bonding. Although no experiments were conducted, the content accuracy was ensured using standard chemistry references. While designed for CSM361 students, the website can also benefit other chemistry learners as a supplementary learning resource.
Finally, I will conclude by summarizing the main outcome of our study and our recommendation. Firstly, principle and generalization. Our results show that molecular properties are mainly controlled by how orbitals interact and how electrons are distributed. Theories such as hybridization and molecular orbital theory remain reliable in explaining molecular shape and bonding. In addition, presenting this concept digitally make them easier for students to understand. Secondly, limitation and practical implication. Although classical models work well for many molecules, they are not perfect. They cannot fully explain molecules with expanded octet or transition metal complex. Also, visualization tools are based on theory and may not completely reflect real experimental behavior. Theoretically, this study shows that combining valence bond theory, molecular orbital theory, and electron density analysis give a deeper understanding of bonding. Practically, digital platforms help students visualize molecules better and increase engagement in chemistry learning. Lastly, conclusion and recommendation. In conclusion, presenting orbital architecture and electronic landscape digitally helps students understand molecular structure more clearly. For future work, we recommend expanding the platform with more molecular example, interactive 3D models, and connection to experimental data to further strengthen learning outcome.